Determine the graph of the derivative function given the graph of any function. Alright, so here we're given a function. It looks like a piecewise function with 3 linear pieces, and we're being asked to sketch the graph of the derivative. Well, first thing to point out here is that we have 2 corners, which means the derivative does not exist at these 2 x values, x equals -2 and x equals 0, since there would be a vertical tangent line. So therefore, we know that at x equals -2 and x equals 0 on our function, those points will not be filled in because they don't exist. Alright, let's look at our first chunk. Our first chunk here is going to be this blue piece right here. And this blue piece covers the interval -∞ to -2 for our x values. Now, since it's a linear piece, we know the slope is constant everywhere. So, if we find the slope of this linear line, every point on our derivative graph will have that slope. Now, let's see the slope. We can use rise over run, so we can come down 3 and then over 3. So the slope of this particular line segment is going to be -3 over 3, which equals -1. So that means that over this particular interval on our derivative graph, the output's going to be -1. So we can come in and we can graph that, but remember, at x equals -2, there isn't a derivative. So that means our endpoint here is going to be open. Alright, let's look at the next segment. This next segment goes from -2, goes from -2 to 0. And that piece is right here. This piece is also linear, so we can go ahead and use rise over run. And we are going to go up 2 and over 2, which means our slope is going to be 2 over 2, or +1. So on our derivative graph, for all the x values in between -2 and 0, our slope, or our output, is going to be 1. And again, our derivative does not exist at x equals -2 or x equals 0 because of those corners. So then we'll just fill in the dot, and I just realized I put that at 2, not 1. So let's just quickly move those down. Sorry about that. Was not paying attention. Alright, so now they're at a slope of 1. And next up, our third piece. Also linear function, so we can go ahead and we can find the slope of this piece by using rise over run again. And if we go down 2, so -2, and then if we go over 4, we'll wind up at a point, meaning this particular slope will be -2 over 4, which gives us a slope or an output of 1/2 on the interval 0 to infinity on our derivative graph. So again, at x equals 0, the derivative does not exist, so we need an open circle there at 1/2, and it'll be 1/2 from 0 to infinity. And there you have it. We have just sketched a derivative, or we just sketched the derivative of the function given. Alright, we're going to do the same thing, except we have a different function here. We do have a piecewise function here, but there are only 2 pieces. We appear to have a quadratic piece right here, because this forms half a parabola. And then we have a linear piece right here. Alright, so with the parabola piece, we can do the same thing with our polynomial. And we can see here that we are going to have a really big negative slope here, but we're working our way down to have a really itty-bitty slope. So we'll just casually get smaller and smaller, or decrease less and less and less, but still decreasing, just not as much. Now, when we get to these connection points, we can see here that we are going to have a cusp, which means at x equals -1, we are not going to have a derivative. And then looking at our next function, this is a linear function, so we can do rise over run. So let's see, it goes through 0, 0, and then we can pick a point up here. Let's see, it's going to go through 2, 4. So that means rise over run, we're going to go up 4 and over 2, so this slope is going to be 4 over 2, or just 2. So since we have a definitive slope for the linear function, we can come ahead and on the interval -1 to infinity, we can have an output of 2. So -1 all the way to infinity. Boom, great. Now, for the first piece, the parabolic piece, or for our quadratic function, this is going to happen over -infinity to -1. Unfortunately, we don't know what the slope is. But as we talked about in previous videos, when we take the derivative, we go down a degree. So if we start with the quadratic function, if we go down a degree, we know it's going to be linear. So therefore, we can just come in and we can sketch a linear function. And again, we don't know the exact slope, so I'm just going to kind of guess or sketch that it's going to be something like so. There you have it. That is just a sketch of what this particular graph could look like. All right, and finally something a little bit more fun. We want to sketch the graph, but here we have a complicated function. We have a rational function here that has 2 vertical asymptotes. Now, just like with polynomials, we probably want to first start out by figuring where the turning points are, or any spots where we would have a horizontal tangent. In this particular graph, there's only one turning point here, and we're going to call that at x equals -5. So we know that on our derivative graph, that turning point will become an x-axis. So let's see. On our first piece here, our slope is going to be negative. On the second piece, or the first half of the second piece, the slope is going to be negative, and then it's going to turn positive. And then our last piece is going to be negative again. All right, so let's see how negative or how much of a decrease is going to be. So starting all the way on the left, well, it looks like we are almost horizontal over here on the left, but not quite. It's flat-ish, so that's going to be a really little negative slope. But then again, we can see we get larger and larger and larger and larger and larger and larger and larger because we basically just fell off a cliff because there's a vertical asymptote there. So over the interval -infinity to -1, we're going to start off really close to 0 and then shoot all the way down to -infinity. So for example, our graph, the derivative function, is going to look something like this, and increase a lot and shoot. Boom, done. Now, in this particular case, it does look as though this piece of the function has a very similar shape to the graph of the derivative. And that's fine. It can. In this particular case, it does. All right, moving on to our next piece, we can see that we have a super big decline here. So we're going to have a really big negative slope, or a point that's really far away from the x-axis in the negative direction. But eventually we're going to end up at 0, so we're going to have a really bitty little slope. So we'll just decrease, 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 decrease until we get to 0. Again, starting off really far away, so like somewhere down here, and then eventually working our way up to 0. And I need to fix my graph. I was a little bit off with this piece right there. So let's just move that back over to -1. There we go. And this guy will pick up over there at 1. Whew, there we go. All right, and this guy can then kind of come up until we hit the turning point. And then at turning point, we are positive. So the slope's going to be positive, but just a really little bit positive. But by the time we get to the end, it's going to be really big positive. So just casually getting larger and larger and larger, which means we are going to shoot up all the way to positive. Oh, shoot all the way up to positive infinity. All right, and then the next piece, we can see that we start off with a really big decrease, and we're going to end up kind of flat, so a much smaller decrease or much less of a decrease, so we'll work our way down the function. So again, it looks as though we are going to start off really far away from the x-axis in the negative direction and work our way back up to it. So zoop and zoop. And there we have it. That is a sketch of the derivative graph. All right, folks, and that is it. That is determining the graph of the derivative given the graph of any function.